Good morning, Physics 30. I hope you guys are having a good day today. Welcome to our lesson on mass energy equivalence. So our mission for today is we're going to be looking at why nuclear reactions have such a ridiculous amount of energy released. And that is all due to mass energy equivalence. So this is where Einstein's E equals mc squared equation comes in. I always feel so smart using this equation. So Einstein, he determined that there's a relationship between mass and energy. And you could take mass and convert it into energy, and take energy and convert it into mass. Mind-boggling. So it's known as our mass energy equivalence, and it explains why nuclear reactions release such a ton of energy is because mass is being converted into energy during these nuclear reactions. So your equation equals delta E equals delta mc squared. And you can find that on your lovely data sheets, which you can find right up there in your quantum mechanics, right there. Okay. So delta E, once again, the deltas are important here, is the change in energy resulting from converting mass into energy. Delta M is the change in mass. So this is something that I know it's really weird. Like, we've never done a change in mass in physics up till this point, because it's always been a constant up until nuclear reactions. So we're going to be losing mass throughout our nuclear reactions as it's turned into energy. And c is our speed of light, which is in your data booklet. So, ladies and gentlemen, let's do a quick example with this equation. So what is the energy equivalence of a neutron at rest? So a rest, that tells us that there is no EK that we need to worry about. Okay, so we are looking for the E. Okay, and what is the mass energy equivalence of a neutron? Well, what is the mass of a neutron in kilograms, ladies and gentlemen? Where are you going to find that? Data sheet. All right, I need to pause the video for a sec, guys. I will be right back. All right, we're back. Sorry about that, guys. Okay, so we're trying to calculate the amount of energy, and we need to find the mass of a neutron. Where are we going to find that value? Data sheet, absolutely. So if you go to your data sheet, on the back page, with some of the constants, what you're going to find is a mass section on the back page there. And at the very bottom, you can see the mass of your neutron. So from your data sheet, the mass of a neutron is 1.67 times 10 to the power of negative 27 kilograms. So, ladies and gentlemen, if we were to take this neutron and convert it into energy, the amount of energy that would be released, we would use our delta E equals delta mc squared. So the change in energy, so the energy that's going to be released from the change in mass. So our initial mass here would be taking our 1.67 times 10 to the power of negative 27 kilograms, and we would then be converting all of that into energy, which means we would have 0 kilograms left. And C, from your data sheet, 3 times 10 to the power of 8 meters per second, you would square that value. And once in your calculator with appropriate sig, digs, and units, you would have your 1.50 times 10 to the power of negative 10 joules. So it seems like an awfully small amount of energy, but let's put this into perspective for a moment. Look at the difference here. How many orders of magnitude is that? That is huge, ladies and gentlemen. Huge. For a significantly small piece of mass, you're getting a lot of energy out of it compared to its size. So it is insane. Insane. So, ladies and gentlemen, your mass energy equivalence, this is used to help explain why our nuclear reactions like fission and fusion, they release a ridiculous amount of energy as opposed to a chemical reaction. So where are we going to see these values in reactions? Because when we look at our nuclear reactions, we're dealing with the conservation of mass and charge in nucleons. So let's look at this reaction here for a sec. Well, we've got a mass of 18 on this side and a mass of 18 on this side. Okay, all is good. We go over here, we've got your proton number of 8 over here. 9. It would help if I would write my numbers down properly. There we go. Okay. And so 9 over here and then 9 over here. Okay, we're good. So our conservation of charge and nucleons is still going here. So why are we getting this? Where is this energy coming from? Where is this mass being converted? Well, the reason why is when we're going to be using our standard nuclear notation, so this format, your units for your atomic mass are in what are called atomic mass units. Okay, so U. And 1 U is equal to 1.66 times 10 to the power of negative 27 kilograms. And this is on your data sheet. Okay, so your atomic mass unit conversion is right there at the bottom of your data sheet. Okay, so those are the units of these guys. Now, if we're going to be using these atomic mass numbers, these are going to be rounded to the nearest whole number. Okay, so as soon as we start putting these into kilograms, the mass into kilograms, and we're going to be looking at a more accurate scale, what you will see with them is that the total mass of all of the reactants is always, and now very rarely do we actually say always here, greater than the total mass of all of the products in a nuclear reaction. So this is called the mass deficit, or delta M. And it's this so-called missing mass that gets converted into energy, and it's this energy that is released, which then are harnessed in the form of nuclear power plants or nuclear bombs. So we prefer nuclear power plants to nuclear bombs. Okay, so this is why these nuclear reactions release so much energy, is because mass is being converted into energy. So we're still following the laws of conservation of energy here. It's just a new angle of it. It's pretty cool. So, ladies and gentlemen, we're going to work our way through a practice problem, which is going to look at several different entities here. So we've got radium-266 is going to undergo alpha decay. So let us write out a nuclear reaction. So we have our radium. Well, the mass number is 226. You will get its atomic number from the periodic table, which is 88. This guy is going to be converted into what? I started writing out the answer a little early here. Okay, well, we know it is going to be an X, okay, and an AZ, and it's going to undergo alpha decay, so it's going to release an alpha particle, so helium nucleus. And, well, let's figure out what these remaining values are. So let's figure out the value for A. And, well, the sum of all of the particles on the products has to equal 226. So 226 minus 4 is going to give you your 222 for your mass number. And this Z here, well, 88, we want the sum of all protons to be 88, and we got 2 here, so 88 minus 82 is going to give you the messiest 6 I have written all day. There we go. So, well, now go to your periodic table and look up which element has an atomic number of 86. And ladies and gentlemen, that is going to give you radon. Rn. So, using our law of conservation of nucleons here, ladies and gentlemen, we've got it balanced. Remember, these guys here are in your atomic mass units. Okay? So here, and these are whole numbers, nearest whole number. Well, now let's look at if we have our atomic masses more accurate. Okay? So, the atomic masses for radium-266 is not going to be just 226 anymore. It's going to be, we're going to have some decimal places to deal with here. We've got the mass for radon and the mass for an alpha particle, much more specific. So we're going to calculate our mass deficit. Okay, so we need to calculate our delta M. Okay. Now our delta M is going to be the absolute value of the mass of our products minus the mass of our reactants. So these vertical lines here are telling us our absolute value. Okay. Well, we need to find the mass of our products. Well, our products are the radon and the alpha particle. So the mass of my products are going to be my 222.0175778 atomic mass units. Okay. We're going to add that to the mass of my alpha particle because we want the total mass of all products here. So 4.002603 atomic mass units. And then we're going to subtract that from the mass of our reactants here. Okay. So with our mass of our reactants, we've got our mass of radon here. So our 226, I need to scroll down before I start writing on my face. Can't have that. Okay, so 226 point, I lost my place, 0.25410 atomic mass units. All right, so once you put that into your calculator, we're going to have our mass deficit. Mass deficit, that's a hard one to say. Yeah, say that one 3 times fast. Is going to wind up to be 0.005229 atomic mass units. Well, that seems like a pretty tiny amount of mass. Let us convert this into kilograms because guess what? E equals mc squared requires kilograms and not atomic mass units. So, and we're going to be doing in our next question anyway, so we may as well convert that. Okay, using your data sheet, you are going to see that 1.66 times 10 to the power of negative 27, okay, as your kilograms per 1 atomic mass unit. And we're going to get the value of 8.68014 times 10 to the power of negative 30 kilograms. All right, so with some sig digs, because sig digs are how we roll, let's help if I would write my numbers in the right order here. Let's do that. 8.68 times 10 to the power of negative 30 kilograms. So, ladies and gentlemen, what we've got here, it seems insignificant, a teeny amount of mass. But remember that for each teeny bit of mass, you're going to have a ton more. The amount of energy released is a ton. Like, it's just bizarre how much energy gets released from this. And this is just alpha decay. This isn't even nuclear fission here. The amount of energy released from nuclear fission is ridiculous. Absolutely ridiculous. All right. So, ladies and gentlemen, let's go on to our next question. Keep that number handy. So, calculate the energy released by this nuclear reaction. Well, the energy released is our change in energy, and that is equal to our change in mass times c squared. Our delta M we calculated previously, and C is on your data sheet. So using all numbers from your calculator, ladies and gentlemen, you are going to use your mass from the previous question, which is here 8.68014 times 10 to the power of negative 30. And you're going to multiply that by 3 times 10 to the power of 8, and you're going to square that. And now, with your appropriate sig digs, you are going to get a, whoops, it's supposed to be a 7. It did not turn out the way I wanted it. 7.81 times, how many sig digs did I want? And we'll go 2 sig digs. Yeah, 2 sig digs from our 3.0 times 10 to the power of 8. Yeah. So I'm writing 3 sig digs. Oops. So 7.8 times 10 to the power of negative 13 joules. So, ladies and gentlemen, you also could choose to put this number into electron volts if you wanted to. So, remember, ladies and gentlemen, that look at these orders of magnitude here. Negative 30, negative 13. That's insanity. How much energy is released from that insignificant speck of mass being converted into energy? Isn't that nuts? Nuts. So, ladies and gentlemen, let's convert this to electron volts because we can. Why not? So 1 electron volt is going to equal to our 1.6 times 10 to the power of negative 19 joules per electron volt. And the delta E in electron volts with appropriate sig digs and the whole deal. Yeah, we're going to have 4 point, whoops. If we're sticking with our 2 sig dig thing here, I think it should actually be 3 sig digs. I'm having a moment here, guys. Yeah, it's 3 sig digs, 3.00 times 10 to the power of 8. I beg pardon, ladies and gentlemen. I would have cost myself half a point here. Would you look at that? Would you look at that? Half a point lost on my own practice problem here. So with sig digs in energy, 4.88 times 10 to the power of 6 electron volts. Or if you really want to put it into mega electron volts, you could absolutely do that. Whatever floats your goat. All right. So, ladies and gentlemen, ready for the next one? Hopefully you guys didn't cost yourself half a point on sig digs like I did there. All right. So, ladies and gentlemen, calculate the energy released per nucleon for this nuclear reaction. Well, ladies and gentlemen, we have our energy. Let's use electron volts. We're going to use our entire number, not our rounded number that I gave you, full number from your calculator. So 4882578.75 electron volts. Full digit, ladies and gentlemen. No rounding till the end. How many nucleons were there? 226. Okay, so ladies and gentlemen, we're going to then get our 21604.33 electron volts per nucleon. So let's put this into our sig digs here. So 2.16 times 10 to the power of 4 electron volts per nucleon. Well, ladies and gentlemen, that's a ridiculously large amount of number. Like, how completely ridiculous. That's huge per nucleon in that atom. Not every atom was being converted, every nucleon, was being converted into energy. And that's still a lot. Like, it's mind-boggling. Alrighty, ladies and gentlemen, we'll talk about annihilation a bit here. Now, I know we've already talked a little bit about annihilation, where matter and antimatter are going to collide. They're going to just go disappear and annihilate and do a flash of light and energy. So that is where we have the total destruction of the matter and the antimatter particle. And once again, we can use our E equals mc squared to calculate how much energy is lost with your matter and antimatter annihilation. So just to remember here, your antiparticle, same characteristics. Same physical properties. The only thing that's opposite is the charge. And that is what results in our lovely annihilation. Okay. So what we've got here, ladies and gentlemen, calculate the energy that is produced when an electron-positron pair annihilate. So in this case, ladies and gentlemen, when you see annihilate, is that the final mass is going to equal 0 kilograms because there is no mass left. It's all energy here. Okay? So the mass is gone. All mass converted into energy. Okay. So, ladies and gentlemen, with our delta M, your MF minus your mass initial, where there is no mass. Okay, and recall its absolute value. So that means our delta M is just going to equal what our initial mass is, because all that's going into energy. Well, how do I get the mass of an electron-positron pair? Same place I get the mass of an electron. An electron and a positron, being antimatter to each other, have the same mass. You can get the mass of your electron off your data sheet. Okay, take that value, multiply it by 2, because they have the exact same mass. So our delta M is going to equal our 2 times 9.11 times 10 to the power of negative 31 kilograms, which is the mass of your electron. Electron and positron, same mass. So we're going to get 1.822 times 10 to the power of negative 30 kilograms. So all that mass is going to be converted immediately into energy. Okay. So we're going to take I'm going to put this into our E equals our delta MC squared. Our delta N, beg pardon, 1.822 times 10 to the power of negative 30 kilograms. And I got this random thing there. We'll get rid of that. Multiplied by our 3 times 10 to the power of 8 and square that. And we are going to wind up with, once we've got sig digs and units and all that good stuff. There you go. Energy released from annihilation. All right. So, ladies and gentlemen, I hope you guys found that interesting and got to enjoy using Einstein's famous E equals mc squared equation. So we've got some practice problems there for your workbook. You can give those a try if you like. And then we got some practice problems here for you guys to have a shot at. All right, I hope you guys enjoyed the video. Have a good day. No fires, injuries, or explosions. Talk to you later. Bye.